So now that we've talked about flat map, and now that we've talked about the basic concept of scheduler operators in Project Reactor, let's talk about yet another scheduler operator that works on a range of different Project Reactor reactive types, including fluxes, parallel fluxes, and monos. And we're going to talk now about the parallel scheduler. And this arranges to run other operators in a designated pool of threads intended for computation-bound processing. So what is this method? What is this operator, and how does it work? So the parallel operator will create and host a fixed pool of single-threaded executor service-based workers. At first glance, this sounds quite similar to the new parallel factor method operator we talked about last time, but there's ever so slight differences in how it works. It returns a scheduler that's suitable for parallel work. The size obtained by this is set by a system property called Reactor Scheduler's default pool size. So you can override that if you need to, but by default, it will be the number of processors available to the runtime when the application is initialized, when the process starts up, which is typically the number of cores. So it's kind of funny. There's this thing called available processors, which really is available cores. And that's what it's going to default to. So if you have 4 cores, it'll have 4 threads in the parallel thread pool. This particular pool is optimized for computation-intensive, non-blocking tasks due to its fixed size. And we're going to talk more about this later when we talk about the elastic pools, which are used for I/O operators, I/O operations, and I/O processing. And the key thing to note here is that when you're doing I/O-bound tasks, you often want to be able to expand the number of threads in a pool, because otherwise you end up underutilizing the amount of processing available on a multi-core system. But for computation-intensive tasks, a fixed size works just great. And probably we might get time to talk about that before the quiz. It all depends on what we do. But that will probably end up on a quiz question at some point about why we have fixed-sized thread pools for computation-based tasks versus variable-sized, expandable, adaptable thread pools for I/O-bound tasks. And we'll talk about that when the time is right. So compute CPU-bound tasks, not I/O-bound tasks. That's also same as new parallel that we talked about, the new parallel operator. We typically use this type of processing for event loops, callbacks, other types of computationally oriented work. This is what we looked at earlier, where we're going to take this list of big fractions, turn it into a flux, and then multiply everything in that flux stream by some value. And you can do this in different ways. So this will run everything in the background, and it'll subscribe to run on the scheduler's parallel thread pool, because it's computationally intensive. Multiplying values are computational tasks, not I/O-bound tasks. Notice, by the way, this is very important to remember, from callable is a lazy factory method. So the multiply operation you see here runs in the computation thread pool, even though the subscribe operator comes afterwards. This is a little bit confusing at first. I know when I first was exposed to this with Project Reactor and RxJava, I was like, how is that working? That doesn't make any sense, because subscribe on is coming later. But remember, subscribe on applies to everything up the pipeline of operators that are being called. So it also applies up here. Non-intuitive, but that's the way it works. Now, the other thing to note is that there will be a bunch of threads running the different multiplication operations on the elements of the big fractions flux stream, but only one thread will run reduce. And that's typically the last thread. Whatever the last thread was that completed doing the processing of all the things here, that will then be borrowed to do the reduction, because we only need one thread to do the reduction. This is important to remember. This is what differentiates parallel scheduler from the new parallel scheduler. The difference is new parallel used user threads, so you had to remember to dispose of the scheduler that was created using some kind of destructor-like mechanism like do finally, whereas scheduler's parallel creates a pool that uses daemon threads. and if you recall, the difference between daemon threads and non-daemon threads or user threads are that daemon threads won't prevent the app from exiting even if there's still daemon threads running in the background. So if there are no more user threads and only daemon threads running, say, in the parallel thread pool, then the app will exit, which may or may not be what you want. So be careful. So remember that the good part is you don't have to clean it up explicitly. The bad part is it could exit without things being done. There's a method in the RX Java schedulers utility class called computation that works the same way that Parallel does. Once again, why they chose different names is one of life's great mysteries, but it's also fixed size, and it's intended for computation-intensive and non-blocking tasks. Java has a common fork join pool that's also very similar in that by default, it works for CPU or computation-bound tasks, just like we've been talking about. However, you can modify it with something called a managed blocker, and a managed blocker will then arrange to adaptively expand the size of the thread pool so that you can use it for I/O-bound tasks. It's sort of a little-known fact, but it's helpful to be aware of how that works in practice. So that's the end of the discussion of the parallel scheduler that comes out of the box with Project Reactor. And you'll get a chance to use that in some of the assignments.